Hey everybody, I'm Adam Kraus from UT Austin, and today I'm going to be talking about protoplanetary disks and the planet formation process as we think it happens in binary star systems. So over the past couple of decades, the core story of planet formation has really taken shape. We now know, or at least strongly suspect, the broad strokes of what happens when a cloud of gas and dust turns into a star with its planets. However, you might not be surprised to learn that when you drop another star in the middle of this process, it really complicates things. So my plan for today is not to present neatly tied up stories, but instead to talk about what we're seeing so far and the open questions that some of you might end up working on as you continue onward in your career. To orient you a little bit about what we're talking about and what the end state of some of these things we'll be seeing might be, here on the title slide of my talk, I'm showing an image of a nearby planet hosting system, Kepler 444, where the star on the right hosts 5 transiting planets. They're all between the size of Mars and Earth, and all in very tight orbits, as we'll get back to later. And the star on the left is orbiting around it, and it is itself actually 2 stars that are closely orbiting around each other within a fraction of an AU. So there's a lot of really complicated dynamical stuff that's happening today, and that probably happened during the formation process. And so what we'd like to understand is, why did the planets here survive when there are these stars that are so much larger, that are orbiting around, maybe moving around and changing their orbits, and otherwise stirring stuff up? So to give you a brief outline of what I'm going to be talking about, I can basically break the story down into 4 parts. There's first the story of planet formation and how binary systems might complicate this picture. Then disk occurrence rates and the lifetimes of disks in binary star systems, followed by the dynamical signatures of possible interactions between disks and binaries, which might get into some of the explanations for why the disks might have survived and allowed for planet formation to proceed. And then finally, we'll talk about the final boundary condition for all this. My topic for this talk is nominally about disks and binaries, but these lead to planets and binaries, probably. So if we know what we expect to see at billions of years in age, then it can provide some context for what we're seeing at millions of years in age. And really, to justify all of this, we don't have to go very far at all. We just have to look around the solar neighborhood and realize that the majority of all the sunlight stars around us, and probably the majority of all stars, when you do all the accounting, form in binary star systems. And if you look around us, then just in this 3D map of the nearby volume of the local solar neighborhood, you've got Alpha Centauri, you have 61 Cygni, you have Procyon and Sirius and 40 Eridanus, and a whole lot of stars where we know their names and we talk about their names. And so we are probably going to be talking over the next few decades about whether they have planets, whether they have Earth-like planets, and whether they have planets at all is going to be a big input for trying to understand, do they have Earth-like planets? And if they don't have them, why? So I want to start that story with a little bit of an overview of the planet formation and star formation process, and then by introducing some of the complications that binaries might add to that story. So I'll remind you, the planet formation process really is an extension of star formation. And really what's happening is that a cloud of gas and dust out in space is collapsing and forming one or more or many stars. Then around those stars, you get disks that form planets. So this is a movie by Matthew Bates showing a numerical simulation of what might happen when you take a cloud of gas and dust, turn on gravity and other physical effects, and then see what happens and see what stars form. You can see filaments are forming. These dots are all synced particles that represent stars. They're getting a ton of them forming sort of at this point in the movie. And then they are flying around, interacting with each other, leaving the birth environment. So it never hurts to keep in mind that this is the context that planet formation is happening in. And an isolated star might not actually be that common of a scenario, even if that's what we're talking about. Once you've gotten your stars in the cluster environment, then generally the next step is that because they are collapsing and because they're spinning and angular momentum is conserved, then you get a disk. and this disk is the environment that planets form in. Here I'm showing a couple of images, one of the Beta Pictoris debris disk, which is actually very late stage. The gas is more or less gone, and it's just planets and dust and small bodies. And you can see an image of the planet that is in this system. It's now suspected there are 2 planets there at least, superimposed inside of the image of the disk. And on the right, we have one of the first images of disks that was taken by the Hubble Space Telescope back in the 90s, when they imaged the Orion Nebula cluster and saw a bunch of young stars in silhouette against the background nebular emission. And they can actually see there's a glowing star in the middle and an edge-on disk of stuff that is blocking our line of sight directly to the star. But you can still see the glow of the star above and maybe a little bit below, showing it's not quite totally edge-on, but pretty close. To put some scale on this, then there's a scale bar on the beta pitch image, but these are typically tens of AU to maybe 100 to 200 AU in size. Step 3 is that within these disks, then there's going to be dust. So there's going to be solids of various sorts, and there's going to be gas. And what we expect happens is that the dust particles will collide and grow. You get this bottom-up process of what's called core accretion, where the solids grow into bigger and bigger bodies until eventually you get to planets. And maybe for some of them, they get so large, they can hold on to gas, and you get gas giant planets. So the story is one of collisions and going from dust to pebbles, the boulders, the planetesimals, the planets, maybe the gas giants. And this inset here shows how this process might proceed over time, where in the space of a few million years, then the solids, which are the blue curve on this plot of mass in a test object versus time in millions of years, the solids grow as the solid bodies collide and stick with each other. The gas mostly sticks around for the first few million years and doesn't do much until the planets get big enough to hold on to it. And then they can run away and quickly get to like Jupiter's. For another view of this, showing how it really extends out even beyond the limits of this plot, we can look at this movie by Sean Raymond, showing what happens if you take a bunch of planetesimal objects, and here the color coding is how much water they have. So close into the star, so the x-axis is in AU, they have very little water. Far out from the star, they have a lot of water. And then the y-axis is eccentricity, just to show how things might be getting on, let's say, crossing orbits with their neighbors. And so over the space of tens of millions of years, the small bodies are expected to collide and continue sticking and growing until you eventually, at the end of this movie, get a few Earth-like objects, well, Earth-sized objects that have some amount of water that mostly migrated inward from the outer parts once it was lost into icy asteroids. But by 100 million years, that's really when things start to settle down. So this is another point to keep in mind. We're often looking at protoplanetary disks and saying, this is planet formation. But protoplanetary disks happen or exist mostly for the first 1 million to 5 million, maybe 10 million years. So there is a longer story. And in principle, even our solar system could have planets eventually get onto crossing orbits and collide and make a bigger planet, or maybe grind down to a bunch of small stuff. So planet formation never really ends, maybe is the punchline here. So I would argue, after describing these steps, it's useful to think about them in terms of ages and in terms of what they look like. And this is classically described in the class system of SEDs, where you have class zeros, where you don't really see a star yet. You just see thermal emission from the protoplanetary core. But then eventually you get a star in the middle with a disk around it, and mass from the envelope and from the core is going down onto the star via the disk. But you still mostly see emission from the envelope and the disk, and the star isn't really that bright yet. But then eventually the envelope all accretes downward to the disk and then inward via the disk to the star, so that most of the mass is in the star rather than the envelope. Then that would be the class 2 stage, where you still have a protoplanetary disk, but most of the mass is in the star, and the star is mostly what we see. Then finally, you have the class 3 systems, where at that stage, the gas in the protoplanetary disk has gone away. All you have left are whatever planets you form and solids. And then things can continue colliding and sticking, or not sticking, and grinding down. But by this stage, what we think of as the disk is largely gone. And here the ages are sort of 10 to the 5 years at class 0, 10 to the 5 to 10 to the 6. So the first million years is class 1. The first 1 to 10 million years are generally class 2. And eventually, any given object will lose its disk and become a class 3. And that happens generally for the last ones by about 10 to the 7 years. But more commonly, probably a few million to 5 million years. And the reason I'm introducing this is because we can talk about adding binaries now and talk about at what points in this process different effects introduced by the binary companion might cause changes in the story. And so we're going to go through basically a litany of obstacles. This is going to be a little depressing because it's all going to be things that the binary does that seem like they should stop planets from ever forming. And obstacle number 1 is that the binary will tidally and dynamically sculpt the disk. These plots show a couple of numerical simulations of what happens if you simulate a disk, you put down a bunch of test particles, they're basically like planetesimals or like dust, and then you add 2 stars, make them orbit around each other, and turn on gravity and see what happens. And on the left, we see what happens if you have a close binary inside of a disk. And on the right, we see what happens if you have a wide binary companion outside of a disk. And in both cases, they truncate it to about either 3 times the binary semi-major axis or 1/3 of the binary semi-major axis. Nothing has, tides mean that nothing has a stable orbit within those regimes. So this means that there's a pretty broad range of orbital radii where planets can't form because there's no disk there to form them out of. And that's the first obstacle, sort of limiting where planet formation might occur. But even in the parts of the disk where you do still have the disk actually there, then the tides of the binary system add another complication, which is that they stir up the velocities of small bodies with respect to each other. So the right shows a schematic view of what's happening in the simulation of a disk around a binary. This is Kepler 34 as imagined at early times when its circumbinary planet was still forming. And on the left, it shows 2 cases. What happens when you allow for the tidal stirring, tidal interactions between the binary and each individual object, or you don't. So on the top, you have the velocity of 2 objects when they collide with each other as a function of their orbital radius at the time of collision. And you see that most things have a low velocity. They sit down near the base of the y-axis. And this is important because if you model this in terms of collisions either accreting, so the 2 collided stick, or eroding, they collide and break down to more smaller objects, then small collision velocities mean they accrete. Large collision velocities mean they erode. And most of these are accreting in the top case where you don't have the tides. Once you turn on the tides from the binary, then what happens is that the planetesimals start getting tidally nudged onto eccentric orbits, onto inclined orbits. These are what are shown in the bottom panels on the right. And when they collide, their relative velocities become larger. So then most of the collisions actually don't make something bigger. They just grind down what's there and make it smaller and smaller. So this suggests that pretty quickly you expect planet formation to get shut off because whatever's there just gets ground down back into dust and then eventually removed from the system. And so you might not make planets, even if the raw mass is there. Obstacle number 3 is that the binary should lead to, we think, relatively fast dissipation of the disk. So your lifetime and your duration where the planets can form probably isn't that long. And so this cartoon shows the classical picture of what happens when you have a star and a disk seen in profile. And what happens is the UV and X-rays from the star should be hitting the top and bottom of the disk and driving photoevaporation of material off of it. Far out from the star, if a high energy photon goes through, it'll evaporate stuff straight out of the system. Close into the star, deep down the potential well, there probably isn't enough energy being added to drive this material all the way out of the system. So probably what happens is it'll get heated up and get sent outward, but eventually it'll accrete back down on the outer part of the disk. And then because mass in a disk moves gradually inward, you get this conveyor belt of stuff will get sent out, but won't actually escape the system for the most part. So a disk can last for a while. But if you add a binary close in and then take into account that the binary is truncating that disk due to its tides, then what actually happens is you end up directly exposing the outer part of the disk that previously was mostly shielded by that inner part of the disk, so that the outer part of the disk is taking the full brunt of that photoevaporative flux. And so it should rapidly boil away, we think. You can see simulations of this in a paper by Alexander 2012. And so we think that this process maybe takes 10 to the 5 years, not the 10 to the 6 to 10 to the 7 years that disks last if there's a single star there, such that the inner part of the disk can shield most of the mass from being evaporated away. And finally, obstacle number 4 is, even if you have a planet that manages to form and grow and do this within the time that the disk goes around, then eventually over timescales of billions of years, the planet will have long-term secular interactions with the binary that also might drive it onto an unstable orbit and kick the whole planet out of the system. And so this figure shows a simulation of this in the Alpha Centauri system, where a bunch of test particles were dropped to represent planets in the context of the binary orbit. And then time was turned on, gravity was turned on, and everything orbited, and they waited and saw which planet, which test particle survived. It actually turns out that the only ones that survive are the ones either very close in to one star or the other, or very far away outside of both stars. So this is kind of a reflection of the truncation that happened at early times as well. But with the added caveat that even within those regimes, the orbits of the planets do evolve, and eventually a lot of them will be driven into a state where a resonance might kick up the eccentricity higher and higher until the planet is kicked into a star or kicked out of the system entirely. So you deplete your planet population, or if you have a multi-planet system, then you might end up instigating the collisions between the planets to where they destroy each other. Maybe like only the biggest planet gets left behind at the end. So this means that planets, if they form, should be in restricted ranges of parameter space and should probably occur at a lower occurrence rate. So this is a really depressing story overall. There are all these obstacles. So you might stop and ask, like, why do we expect there to be any planets at all in these regions? This seems like it should just say, binaries, bad place for planets. Why are you bothering to look? But we do find them. So, and I'll get back to this later, we actually find quite a few of them, if not as many as we expect. So and so we want to go back and look at these steps and ask which of them are actually influencing planets, which ones aren't, and can we look at this process in different time steps and ask what is the process of going from a nominally identical case between a single and a binary at time of 0 to them being very different by billions of years. And it helps that these processes occur at different stages of this process. So disk truncation starts early when you have the disk, but by the time the disk goes away, obviously it doesn't really matter anymore. Planetesimal stirring probably takes a while to really matter. So it really only kicks in the class 1 stage at, say, 1 million years or so. And then it lasts up through sort of the class 3 stage. Once you're done growing your planets by tens of millions of years, then the stirring of them matters less. The enhanced photoevaporation matters at the class 2 stage and basically just shortens your window for planet formation. And ejections happen at the class 3 stage and beyond. And so for those of you who are thinking about how you might work on this, you can cast this in terms of looking at different kinds of systems and asking what are the demographics when different amounts of these different processes have occurred. And so you can look at protostellar disks. Disks early on, when there still is an envelope around feeding onto the disk at the class 1 to get an early view. Or you look at protoplanetary disks during the class 2 stage to see what's happened later on, probing more of not just truncation, but also planetesimal stirring. Or you can look at debris disks when the gas is gone already, and all you have are whatever planets or planetesimals that were formed colliding with each other, grinding down, telling you there's small bodies there and they're colliding. And then you can ask, well, how fast are they colliding and how many small bodies are there? And finally, at the very end of all this, you can look at old planetary systems at billions of years in age and ask, what do they look like? And this is sort of the final boundary condition. And as I noted, the reason we want to do this is because despite all these obstacles, planets are being found. So this shows in the lower left, the Gamma Cephei system, which is an RV discovered Jovian mass planet that is in a 20 AU binary system. And on the right, we have Kepler 16. Upper right is Kepler 16, which is a very close eclipsing binary system that itself has a circumbinary planet that transits both stars at different times. This was one of the early discoveries out of Kepler. So this raises the question, why do some planetary systems successfully navigate this series of obstacles and which ones don't? And what can this tell us about all these processes? And connecting back to the very start, what can this tell us about which nearby stars where we really want to study planetary systems in great detail might have planets or might not have planets? I always cast this, if nothing else, in terms of the question, does Alpha Centauri have planets or not? We're looking for them in a ton of different ways, but the thing that we don't necessarily always grapple with is that Alpha Centauri has a binary companion basically at the orbital radius of Saturn, and it's eccentric, so it actually swings between the orbital radii of Uranus and maybe down close to Jupiter's orbital radius. What does this do to the planets? We're not sure yet, so we should figure that out before we do something like send a space probe there to study the planets, as the Breakthrough Starshot project has talked about. So to get into the story, I think we want to look at this sort of in roughly chronological view, but also in view of increasing nuance until we get to that final stage. We want to start with the impact of binarity on just the existence and the lifetime of protoplanetary disks during the planet formation process. And this has been a story that really emerged over the last 25 years as we've gotten really good at identifying stars with disks, and as we've gotten better at identifying stars that are binaries, then we combine the two. So we know how to find disks by looking for one of two main signatures, either accretion, so mass falling onto the star, which is signified by things like an ultraviolet excess, or by emission in the Balmer series, or emission of hydrogen lines, and certain other lines that tie to outflows, like I show on the left, or by identifying an infrared excess, because the light from the star is heating up dust in the disk, which then re-radiates that light at longer wavelengths in accordance with its equilibrium temperature. And so, in particular, the Spitzer Space Telescope really revolutionized this by giving us a complete census of disks within all the nearest star-forming regions by looking for these infrared excesses out at wavelengths of a few microns to tens to hundreds of microns. So by this point, in some place like the Taurus Oritis star-forming region, which I show here, then we probably know most of the disk hosts by now. This should cue some uncomfortable silence asking about completeness for disk-free stars, because it actually turns out that once a star doesn't have a disk anymore, it doesn't look that much different from most of the other stars in the Milky Way. So it has been pretty hard up until now to figure out where are the stars that already got rid of the disks. Gaia is helping a lot on this front, though. So it's really exciting that I think as people probe through the Gaia data, this question will probably get resolved in the next few years, and we'll have a really complete census of the stars, disk or not, in all of the nearest star-forming regions. The parallel to this is to ask, once we know if there's a disk or not, how do we know if there's a binary or not? And the usual way we answer this is with high resolution imaging, or sometimes with radial velocity monitoring. And I think for most of the results I'm going to be talking about today, adaptive optics imaging has been the core that locked down which stars are binary and which stars are single, along with some spectral imaging from space telescopes like Hubble, and some RV monitoring. And soon, I think it's interesting to stop and ask, Gaia astrometry will tell us all the binaries in the nearby star-forming regions without any further observations needed. So what will happen when we go from having AO imaging of hundreds of stars to having Gaia astrometry for tens of thousands of young stars? And what will that do to our sample sizes and our ability to probe nuanced effects? But to orient you a bit, since AO is still driving most of the results we'll talk about so far, then this shows the cartoon view of what happens when you observe with adaptive optics. And specifically, You can think about it as a case where some star or two stars very far away are emitting light. By the time it gets to us, at the top of our atmosphere, it's a nice planar wavefront. And if we could image that nice planar wavefront, we would get a diffraction limited image where the resolution is set by the size of our telescope. The problem is we only have a few space telescopes and time on them is very precious. So most of our observations have to occur from the ground underneath our atmosphere. And so what happens is, in this cartoon picture on the left, as those plane waves go through the atmosphere, they end up passing through a bunch of small pockets of air that are slightly different temperatures or densities or humidities. And those pockets end up acting like lenses to deform the wavefront. So by the time the wavefront gets to our telescope, it looks like this corrugated surface. And if we image it, we get something like what you see over on the right with this speckle mess, which is what happens if you image a star through the atmosphere at very high speed. If you take a long exposure, this averages out and gives you a Gaussian-shaped, scene-limited image of a star. With adaptive optics, what we do is we measure the shape of this corrugated surface and deform a mirror in the opposite sense of it. So push the mirror out or pull the mirror in so that the different parts of the wavefront, when they bounce off that mirror, all end up having their path lengths change so that you get a nice planar wave out. And then we send it to our camera and we take an image, we get back a diffraction limited image. So on the right, you see this happening where if the top is showing the wavefront as it appears at our telescope, then our measurement of it, which isn't quite perfect, we can't measure the smallest deformations, but then if we measure those deformations and correct them, we get back something that looks not that far from a planar wave. The image below looks like a diffraction image with area rings instead of this blobby mess. And using this, we've now been able to image hundreds of young stars in nearby star-forming regions. So I've picked one example here where my collaboration has used Keck Observatory to observe over 400 young stars over the past, now closing in on 15 years. And these are young stars in nearby star-forming regions. And so what we get out are images, like I showed on the previous page, and I'll show more images later in some cases, test cases. But we get basically a contrast and a projected separation. Then we can talk about things like what is the detection limit? And we can talk about what we've detected, putting them down as points in this contrast separation parameter space. Or we can convert this into masses and separation in AU. We talk about like tens of Jupiter masses up to solar masses. And then the detection limits saying what could we have seen down into the brown dwarf regime or even the planetary regime for a lot of these observations. And so we can then parse these binary populations that we find and ask, for example, how are they different between the stars that have disks and the stars that don't? Or how do they differ as a function of the separation of the binary in terms of whether they have a disk or not? And this has been a story that people have really worked on for about 25 years now. So I'll run through some of the major realizations that we've had. And it starts back in the 1990s when, for example, Jensen et al. In 1996 observed a bunch of binaries that had been found, mostly with larger separations. There wasn't that much high resolution imaging available at that time. And they used the flux at wavelengths around 1 millimeter. So that's basically emission from the dust in disks as a proxy for saying if they have a disk or not, and some indication of its mass. And here in this plot of the flux as a function of projected separation in AU, where filled symbols are detections and open symbols are upper limits, then you can see that there were a lot of detections around binaries across the full range. But this was the first indication, maybe, that there were more disk hosts at wider separation binaries, or at least maybe that there were more massive disks in wider separation binaries. And maybe there are fewer or less massive disks among the tighter binaries, but you find disks everywhere. Around the same time, Ghez et al. In 1997 observed a sample of them and constructed detailed spectral energy distributions to probe their disk properties in distant systems. And for example, they showed in the case of df tau, in this plot that is the emergent flux as a function of wavelength, then df tau has excesses out past 1 micron or 10,000 angstroms, showing it has a disk somewhere in the binary system. We'll get back to that in a little bit. Whereas V773 tau didn't really have an excess, showing it didn't have a disk. And these were used as evidence that yes, binaries can at least get to this stage and have planet-forming disks. So it's not hopeless to think about planet formation occurring in even fairly close binary systems. These were on scales of 10 to tens of AU. By the 2000s, there were much larger samples available, looking at, say, infrared excess as a function of projected separation, or looking at accretion rates as a function of projected separation, like these results from White and Ghez 2001, where they were still limited to like tens to hundreds to thousands of AU, but they were able to show that yes, disks are in fact pretty common. The story got more nuanced and more intriguing by the late 2000s, when people started to realize, well, when surveys were able to get higher spatial resolution detections of binaries, and people realized that maybe this lack of disks among close binaries might really be a thing. Specifically on solar system scales, then it seemed like there might have been fewer stars with a large excess, shown on this plot here from Cieza et al. 2009, of infrared excess as a function of separation here in arc seconds, where they showed that there's an excess containing a disk for many wide binaries and a few close binaries, but the stars without excesses were maybe concentrated among the closer systems. And then here, I think the light blue points are the single stars, so there's plenty of both among singles. And this trend really emerges in results that I added to things a few years later, where we did a detailed accounting for one star forming region of doing a uniform binary survey, like the results I talked about a little bit ago, and then cross-correlating that with the final results of Spitzer, saying which stars had disks or not. And specifically, by pushing down our binary surveys down to a few AU, we're able to really probe the scale that corresponds to our own solar system. And here, what I show is a plot of disk frequency as a function of the projected separation of binary systems in AU. And then the blue is single stars, and just as a band across the top to show their occurrence rate. And the red points are the binaries. And what we really find is inside of about 40 AU, the disk occurrence rate for these binaries in Taurus at an age of 1 to 2 million years is something like a third. By the time you get out to many tens of AU to hundreds of AU, the disk fraction is more like 80 to 90%. And for single stars, the disk fraction is right around 80%. So this is interesting because it suggests that even when single stars and wide binaries have their disks, have almost all of their disks still, then the close binaries have gotten rid of about 2/3 of the disks in total. Not all of them, but the occurrence rate is suppressed by about a factor of 3 inside 40 or 50 AU. So this raises the question, when does this happen? Taurus isn't the youngest region we know. So we can also look at regions across a range of age, from Ophiuchus, where most of the stars are still 1 million years old or maybe less, out to Upper SCO and moving groups like Theta Pit or Eta Ka or TW Haya. And we can show that the disk fraction specifically for close binaries in these systems starts low in Ophiuchus. And this was confirmed by Cheatham et al. 2015 with a much larger sample than we had available in 2012. It starts low and then stays pretty constant until sometime by 10 million years or so, it must drop off to 0 like everything else. But it appears that disks, close binaries having lost the majority of their disks, is an effect that is locked in within the first million years, which is interesting. And then it doesn't really change that much from 1 to 10 million years across the class 2 stage. There is one point that's also worth making regarding the single stars, which is we typically see disk frequencies as a function of age, talked about in terms of disk frequencies for total population, not dicing up singles versus binaries. And here in this plot from Hillenbrand in 2005, the disk frequency as a function of age was plotted with all these symbols and suggested to decline linearly. But what we realized afterward is that if you take these points and correct them by removing those binaries that lost their disks early and looking at only the singles or singles plus wide binaries, it actually increases the inferred disk frequency to where the frequency stays up around 80 or 90% for the first few million years pretty constantly, and then it drops off pretty quickly. So this also has implications for single stars having overall more time and a more uniform length of time to form planets in their protoplanetary disks. It is worth noting there's a caveat here. Even our binary surveys couldn't get inside a few AU. So I think it's still an open question. What happens when you have a binary at 1 to 2 AU or at 0.1 AU? We haven't had that sample available yet, but Gaia and larger radial velocity surveys might open that up in the near future. Finally, I'll just note that this sort of very empirical observation we made based on our results also agrees with a model from Alexander and Armitage 2009 of exactly what happens if you consider single star and binary star disk evolution differently and perform this correction. And you find that the disk fraction stays near 100% until it plummets relatively quickly. So, okay, the punchlines out of part 2, out of considering distant distance, are pretty straightforward. It seems like many young binary systems host disks, and for those wider than the size of our solar system, so wider than 50 AU, binarity might not even matter. Whereas on solar system scale, disks still exist, but it looks like 2/3 of close binaries don't host disks, even at times when almost all of the single stars and wide binaries do. And it looks like this pattern is baked in early. Even the youngest populations have a lower disk frequency among close binaries, which raises the open question, why do 1/3 of disks survive? So this brings us to the next part of my talk, when we're going to look at some of the dynamical signatures of interactions between the binary and the disk, because these interactions are presumably what drives whether the disk forms and survives or not. And this is basically just going to be a tour of all of the phenomena that we've seen so far. And to start with a relatively straightforward one, it appears that disks survive in some fairly extreme binaries, which I would not have necessarily predicted ahead of time. So if we look at the orbits of young binaries, where there are disks or where there aren't disks, then we can get a sense of whether the disk existence correlates with the properties of the binary system. The full samples are only just now becoming available, for example, in recent papers by Schaefer et al. And by Rizzuto et al. But if you look at some individual cases, you see pretty extreme systems. So this is the system Rotsess 47A, where the binary orbit is shown here. The primary star is at the position of the asterisk. And the semi-major axis is 5 AU, so fine, it's Jupiter size, but it has an eccentricity of 0.82. So it has a periastron passage at 1 AU and apastron out at something like 10 AU. And if you think back to our discussion of truncation, this means that a disk around each individual star would be truncated at a fraction of an AU. And the circumbinary disk probably is truncated at something like 30 AU. So you have this huge gap between the outer disk and the inner disk, and everything is exposed to light from these stars that should be evaporating away those disks. So why does that very small disk around each star and the very tenuously bound circumbinary disk survive? It's unclear, but apparently the universe does it. So this is going to be one of the types of inputs we want to have in the future, is how many of the eccentric binaries versus the circular binaries have their disks survive. We can also look at things like which star has the disk. So these are results from Allen et al. 2017 on the left and Sullivan et al. 2020 on the right. And in both cases, you can ask Lisa Prado more about these on Tuesday during the panel discussion if you want to know more, since they come from her research group. But the brief summary is that Allen et al. Showed that in the DF tau system, where its orbit is shown in the middle, then the primary star appears to have a disk and accretion. So it has a UV excess at short wavelength and an infrared excess at long wavelength, whereas the secondary star appears to have no disk at all. But these are sitting there within about 10 or 15 AU of each other. And so why did one end up with a disk that lasted this long while the other did not? Whereas other cases, and so these are a couple of wider systems, S Chronostralis and VV Chronostralis, look like they both still have disks, because you can see accretion here indicated by bracket gamma emission in these spectra from both stars. So at least in these cases, it appears both stars have the disk. So a unified story hasn't yet emerged as to why, even if there is a disk, Might be around the primary or the secondary or both. But the samples are growing. For example, you can look at Aitchison et al. 2019 for a additional study of this in the millimeter for among binary systems. So looking at disk masses and distant distance. We can also see more and more cases of disks actually being truncated by binaries and directly resolve it. And so this was first seen in the 90s. So you can look at Jensen and Matthews 1996, for example, where if they looked at the SED, they saw disk hosting binary systems often lacked excess emission at short wavelengths, indicating that there was an inner gap cleared by the circumbinary disk, or cleared in a circumbinary disk. So there was only cold stuff far from the stars. A more recent example is COTU Tau 4, where modeling suggested that there was an inner 10 or 15 AU gap that maybe was attributed to active planet formation, until we realized that no, there's actually a binary star there, and it's actually that the binary stars are completely clearing out this gap. And actually neither star has a disk around itself. It's only material orbiting around both. And this was modeled by Nagel et al. 2010, shown in this SED on the bottom. So energy is a function of wavelength, showing that you just see the star out to almost 10 microns, and only then do you just see infrared excess from the disk. So this raises the question, why did the disk survive if it's directly exposed to radiation from the central star? I think this is still a question people are arguing over. It's also worth noting that as millimeter observatories have improved, first with the submillimeter array, and then later with ALMA, we've gotten huge boosts in spatial resolution and in sensitivity. So disks can now be directly imaged in the emission from their dust and gas. So these observations yield masses and yield disk orientation, then give a detailed view of their structure. HL Tau, which is shown on the left here, was only announced about 5 or 6 years ago now, and it started a revolution that is still ongoing with results such as from the D-Sharp survey, which I show at the bottom here. So this is a binary system where you can see AS205 North looks like just a standard disk. AS205 South has a disk with a bunch of structure in it, these rings that suggest something interesting is going on with planet formation, or at least with something like density perturbations within the disk. And these are part of a 1.3 arcsecond, or about 150 to 200 AU binary. We can see from the resolution here that it's now becoming possible to spatially resolve the circumbinary disks and even the emission around individual stars. And so this is being looked at originally at low resolution by Jensen et al. 1997, and then Harris et al. 2012 updated with higher resolution. There have been more updates since, doing things like using the submillimeter flux, which is a proxy for disk mass, as a probe of disk properties as a function of binary separation. So this plot shows the flux coming out of a binary system as a function of projected separation AU. All the single stars are in this separate window off to the right. But then what happens is that you can see as the binary separation drops, then the amount of flux in the millimeter drops. So at thousands of AU, then the distribution is basically indistinguishable from single stars. At hundreds of AU, it drops by a factor of 5. At tens of AU, it drops by another factor of 5. Then these pink points are a couple of oddities where there are very massive circumbinary structures specifically that are sort of a separate topic, but one that is interesting to dig more into if you're curious about that. So this raises the question, maybe disk mass varies by submillimeter axis. So this could explain why close binaries maybe lose their disk quickly if they have less mass, and might be reflected in something like what the planets that come out the other end look like. However, as we get more into the details, and as ALMA gives us better and better spatial resolution, it's actually looking like what's happening is that the binaries might be truncating the disks, but when we image them specifically in dust emission, we're actually not seeing that truncation. We're seeing a combination of that truncation and then solids gradually migrating inward. So that's why the disks are faint, because they're small and optically thick, because all the solids are in the middle, rather than being much larger with a larger emitting area. This was realized by Binarity et al. 2009 when they directly resolved a bunch of disks and binaries. And here in this plot, they show the radius as a function of the radius of the disks as a function of the projected separation of the binaries. And this R over A of 0.3 is that nominal tidal truncation radius that we expect the binary orbit to truncate the disk at. And most disks fall below that, more a ratio of 0.2 or even 0.1 or less between the disk size and the binary size. And they interpret this as just being a sign that all the dust is down to the middle fairly quickly in these binaries, more so than in the single stars. Whereas in the older regions, and so this was a realization by Barenfeld et al. 2019, the connection between disk flux and binary separation appears to disappear, because then it seems like the solids have migrated inward for all disks, singles or binaries, and made the dust disks small. Disk alignment is also a potentially really exciting way to probe what is going on with disk evolution and disk survival. And so an important question to ask is, how dynamically active is the binary and planet formation process? Do the stars move around? Do they scatter off of each other? If things are tilted, like orbiting on a tilt compared to each other, then you get much stronger tidal interactions and everything is nicely coplanar. And so the amount of alignment between orbits and between disks and between stellar spins can tell us some combination of how strong are these tidal effects once they are misaligned, and how strong are the environmental interactions based on things interacting and kicking themselves onto, say, misaligned orbits, or torquing onto misaligned orbits or orientations. And so you can see, and so in the lower right here, I show results from ALMA from Jensen and Akis in 2014, where for a binary system that's separated by a few hundred AU, then the binaries are actually quite misaligned with each other. So the panel on the right is specifically showing the velocity field of those stuff. So red is disk material orbiting toward us, away from us, and blue is disk material orbiting toward us. So the lower disk around the lower star is maybe tilted at about 45 degrees in this image, whereas the upper disk is tilted past 90 degrees. So these are clearly misaligned with each other. And if you look at this more generally for binaries as a function of projected separation out at hundreds to thousands of AU, it seems like there is at least some misalignment in most cases, but maybe not all that much. Some systems are misaligned by many tens of degrees, like these few up at the top, but more of them are misaligned by a few tens of degrees. So they're moderately aligned with each other, but not strictly aligned. It's now becoming possible to also look not just at whether, if you have a binary with two disks, are those disks aligned with each other, but how are they aligned with the binary orbit itself? And this has really just emerged as Gaia has given us super precise astrometry of individual stars. So we can use the motion in the Gaia proper motion of, for example, GI tau with respect to GK tau to measure its orbit. These are separated by about 15 arc seconds total. And yet that motion is significant enough to fit an orbit to it, or at least a family of orbits, and show, for example, in this lower image on the left, that there are a bunch of orbits that all look close to face on. The inclination distribution is sort of centered at 160 degrees with allowed inclinations of 140 to 180. So up to about 40 degrees off from face on. If you compare this to ALMA observations, so these images at the top from Long et al. 2019, the orbits are from Pierce et al. 2020. If you compare these to ALMA observations by Long et al. 2019 of the individual disks, they also found disk inclinations of around 140 degrees. So it looks consistent with these being pretty close to a line between the disks, each disk with the other disk and the disks with the binary orbit, but maybe off by 10 or 20 degrees, consistent with the story from the last slide. And it's only recently, very recently, become possible to push closer in and look at very close binaries. These are actually inside solar system scales. So these are results from Chikala et al. 2019 for say the HD 98800 system or the AK STO system, showing that for orbital periods of days to a month or so, then actually strong alignment seems to be common, where everything is aligned to within possibly a few degrees. However, for wider orbits, the disk orientation does become less correlated. We even get some polar configurations, like for HD 98800, where the binary is tilted 90 degrees with respect to the disk around it. But there actually haven't been that many studies of, say, a few AU to 10 or 20 AU yet. So the question of how this works for binaries on the scale of our own solar system. It's a very, very tight or very, very wide. I think it's still an open one that people are only just now starting to look at, with the first ALMA programs imaging disks in 5 or 10 AU binaries, where we also have orbits. So the punchlines from this part are that binaries appear to sculpt disks in observable ways. So they carve openings both internal, like circumbinary gaps, and external in terms of truncation. But then we also have to account for subsequent evolutionary processes, like dust grains drifting inward in the disk over time, and interpreting our observations. So this can get pretty nuanced in terms of deciding what our observations tell us. But it does seem overall like disks survive in extreme configurations, such as very high eccentricity, or being directly polar oriented with respect to the binary. So there isn't a clear story that this kind of binary definitely gets rid of all its disks. This kind of binary definitely keeps all its disks. And it seems like alignment certainly isn't universal. Things are sort of aligned with each other, not strictly aligned, but also not random, it seems like. But tests at solar system scales have been challenging and are only just now starting to become possible. But probing the dynamics of these systems as we get more measurements of orbits and of disks in terms of their detailed orientation will be an interesting question to see at what point do we know enough to forecast backward what the evolution was, and forecast forward what future evolution will be in terms of why these disks survive and how they'll survive in the future. Okay, so the last part of this talk is going to be a short discussion of the boundary conditions, the final boundary condition of this whole question of planet formation and disk evolution, which is to say, what planets do we actually find in binary systems at ages of billions of years? It's been known for 20, 25, 30 years now that you do find binaries among planet hosts. This was observed early on for radial velocity planets. I showed the results for Gamma Ceps from Hatzies et al. 2002 a little bit ago, but also people have imaged stars once they are known to have RV planets in order to look around them for binary companions, and found quite a few. So these are results from McGraw et al. 2007. I also suggest you look at Desidera and Barbieri 2009 and Duchesne 2010 for additional demographic studies of the RV planet population and the binary companions to those stars. So it seemed like at the very least, wider binaries were common. They actually couldn't say too much about close binaries. There were suggestive trends saying that there weren't enough close binaries. But the problem is the RV planet search process, and really most planet search processes, are really complicated if you have another nearby star that's too close to the one you're surveying. If you have two stars there, you can't really parse the spectrum in detail in order to get radial velocities at the meter per second or even 10 meter per second level that you would like to find planets. So it was always a little unclear as to whether this was a selection effect or an astrophysical effect. But this became a lot easier to answer with the advent of large transit surveys, most notably starting with Kepler, because then, sort of by design of the survey, there was almost no bias against binarity, because the telescope had such low resolution, such large pixels. They didn't know when they observed a star if it was a binary or not until after they had found the planet or not. There are still some caveats, and so I won't call this totally unbiased against binarity, but we can control for the caveats. And I'm happy to talk about that more with people if anyone ever wants to hear more. But so the key is that they observed 200,000 stars with Kepler. Now TESS is observing the whole sky. And we can say, once they have found a planet, then we go back and look and say, is there a binary companion or not, in an unbiased, mostly way. And so this has been done by a lot of surveys observing. I'll get more into the other surveys in a few minutes, but a lot of surveys looking at these planet hosts, in part because they also want to vet out binaries and know if there's a binary there, because its brightness contributing to the light curve can influence your measurement of the binary properties, or even make you think you have a false positive or don't have a false positive. So there have been observations of thousands of binaries now, or thousands of planet hosts now, finding hundreds to maybe thousands of binaries. And there seems to be a picture emerging. And so here I'm showing my results from a paper in 2016 saying that, yes, it really does appear that when you have a close binary, then the planetary systems are less common than you would expect. Actually, the punchline here is we are looking at places where we know there are planets, but we find that close binaries are less common. And so this is a plot, specifically a histogram, number of stars as a function of number of binary companions as a function of projected separation in the Kepler planet host sample. And there aren't enough close binaries. This isn't because the close binaries are out there, it's because the close binaries don't have planets, so they don't show up in the Kepler planet host sample. And we can model this in terms of what was expected from the known overall demographics of binarity of sunlight stars, which is the blue curve, and what we actually see, and see this marked deficit between the blue and the red curve inside of, in this case, 100 AU or so. Whereas if you introduce a very simple model, and in this case, if you just say inside of 50 AU, then the binaries get rid of 2/3 of their planets or never form them in the first place. So there are only 1/3 as many close binaries in the planet sample as you would expect. You actually get a curve that matches the data extraordinarily well. And it's interesting that these numbers roughly match what we see in the disk at early times, where inside of 40 or 50 AU, only about 1/3 of stars have their disks, when the wide binaries and the singles almost all have disks. So this seems like an interesting statement that maybe this effect is baked in pretty early. Whereas if you look at wider binaries, and here I'm showing the results from my survey, but also you can look at all the other surveys out there as well, then once you get outside of 100 AU or so, it actually seems like the number of binaries expected is more or less what you actually see. And so it seems like outside of 100 AU or so, the existence of a binary companion doesn't really seem to affect the final boundary condition of whether you have planets there or not. I think there are still open questions as to whether you get the same planet, and do the planetary demographics really match up? The first papers like Zidler et al. 2021 and Lester et al. 2021 are starting to look at those demographics too. But it seems like the question for the wider binaries from a planet formation perspective changes from what is the impact of the binary to why is there not more of an impact of the binary? So it's turning around our studies of those dynamical processes for the wider binaries, which is very interesting in that 100 AU isn't that much larger than the protoplanetary disks that we were talking about not that long ago. We can also get into some of the same detailed study questions for these systems to ask, what are the properties of the system? Why did the planets survive or not? That we asked for the disks. And so this is one case. This is Kepler 444, like I showed on my title slide. And I'll remind you, there are 5 planets around the star on the right. The star on the left is actually 2 stars in a close orbit that are then orbiting around the star on the right as well. And Dupuy et al. 2016 showed in detailed modeling of this orbit that if you measure the motion of the binary companion over time, or really the lack of motion, and then if you measure the radial velocities of the primary star and the companion over time, and the difference between them, you can do a full orbit fit and show that the orbit is basically edge-on, which is interesting because the planetary system was discovered by Kepler to transit. So the planetary system is edge-on. So it does look like there is alignment probably between the binary orbit and the planetary orbit. However, the planetary orbit itself, the binary orbit itself is weird. If you do the fit, you find it's very eccentric. That's eccentricity of almost 0.9. And the periastron approach is at 5 AU. So if you think back to the disk truncation picture we talked about, then given that the binary orbit was probably set by the time the planets were forming and hasn't changed much, then the planets around this primary star somehow formed in a disk that was truncated at 1.5 to 2 AU. So it didn't really have a whole lot of mass there to form planets. And then any circumbinary disk had to be out at, if Apastron is 70 AU in this case, then the circumbinary disk had to be out well past 100 AU. So it raises the question, how did you form those planets? And yet the universe found a way to do it. And so this is like a very strong test of, can the planet formation process be modeled such that the disk survives and planets get made, like we know the universe managed to do. And if you zoom in, you can really see the scale of what had to happen here, where this disk was only 1 or 2 AU in size, this binary companion, and the gray curves are all of it's the allowed family of possible orbits. So the binary companion was swinging in close, truncating this disk, but you still managed to make 5 pretty close in Mars to Earth-sized objects. There is an interesting bit of speculation, though, in that we see a lot of planetary systems out there in the Kepler sample that are tightly packed super-Earths or sub-Neptunes. So they're much bigger and much more massive than these planets, but they don't have a binary companion truncating their disk. Is it possible that these are just a reflection of the same process, making a bunch of planets very close into the star, but because the disk was truncated, you got Marses to Earth rather than super-Earths and sub-Neptunes and Neptunes. So this actually points out how we have an interesting opportunity in planet hosting binary systems. If we know what the binary companion did to the disk, then we are controlling for the properties of the disk billions of years after the disk has gone away, when we can say, okay, what planets came out of that disk? Our alternative is we can go out and find planet-forming disks now, measure their properties, and wait 5 billion years to see what the planets look like. But that's a bit longer than most of us want to spend on one project. So this might be a unique window into the planet formation process and into controlled experiments of planet formation. And an expansion of this by Dupuy et al. That is coming out soon has shown actually for many orbits of planet hosting binaries, they tend to be mostly aligned in that we know with the planetary system, we know that the planets are orbiting edge on to our line of sight because they transit. That's how we found them. So we can look at the binaries and ask, are their velocity vectors mostly radial in and out or mostly tangential, going in a circle around the central star on the sky? And more of them are more radial than tangential. They're not all strictly radial, so there is some tilt between the binary orbits and the planetary orbits. But this is consistent with basically most of them having a tilt of 10 or 20 degrees, not 90 degrees, which is consistent with what we saw from disks earlier. That's a common story I keep on saying. We can also look at much wider systems and start to play the same game. So this is the system of 2 Kepler planet hosts, KOI 244 and KOI 1803, that actually happen to be binary companions to each other, separated by 8 arc seconds. And it turns out both stars have transiting planets. So it says both have planetary systems, both are edge on because they're transiting. And it raises this question, is the whole system aligned? And Pierce et al. 2020 used Gaia data to measure the orbit and fit at least the family of possible orbits to the system. And they showed that the binary orbit is modestly inclined, but it is inclined. So it is definitely not strongly aligned with either disk, but it's only by 10 or 20 degrees, that same number that we keep on hearing it over and over again. So it does seem like even at these scales, so this was out at hundreds to thousands of AU, there is still some connection or knowledge of orientation between the individual planetary systems and hence their original disks and the binary orbit itself. So the punchlines for this last part are that it seems like the suppression effect for planets in close binaries is a good match to the effect for disks in close binaries. Inside 50 AU, you suppress by about a factor of 3. Whereas outside 50 AU, occurrence rates might be similar between wide binaries and single star, which suggests that the binaries don't really have much impact on planet occurrence once they are wider than the solar system. And then the question gets turned around and we ask, why not? There is still a star there, and stars are really big, and stars have tides. And so that's an interesting modeling question. There also have orientation distributions look similar for planet hosting young binaries and disk hosting young binaries. And like with this, we see planets, even some very eccentric binary systems, some very weird binary systems. So somehow planets find a way, and these pose an interesting opportunity to test the impact of disk size on planet properties. So to wrap up this whole story, I think there are a few lessons we can take away from planet formation at a high level. One is, as I said, when there's a binary companion on solar system scales, it does suppress planet formation by a large factor. It's not 100%, but it's over 50%. So this says that something like 2/3 of close binaries, or about 20% of all stars, when you consider what fraction of all stars are in binary systems, fail at one of those steps I outlined at the start of obstacles going from a cloud of gas and dust to a star with its planets. So that's kind of depressing, saying a whole lot of stars out there don't have planets. But the universe has a lot of planets. Kepler has told us there are a ton of planets out there. So maybe the positive way to look at it is that all of those planets are just orbiting the other 80% of the stars. And then we did a bunch of interesting questions to address why are they orbiting those 80% and not the 20% in close binaries. And it does appear that this impact is early and fast. The disk effects are locked in by 1 million years in terms of the disks not being there anymore. And planetary populations at 5 billion years look very similar to the disk population at 1 to 5 million years. So I think this is going to need studies at the early stage in order to directly see this process. And then the studies at later stages are largely looking at the effects of it and trying to tease out if this system if this planetary system survived and this one apparently didn't, why, in terms of those early evolutionary processes. So the disks and its evolution and dissipation really is a key part of this whole story. And so I'll just leave you with this open question. What key features establish which close binaries keep their disks and form planets? I think that will be a rich area for future projects over the next 5 to 10 years. So for the students and postdocs who are listening to this talk, I should be thinking about how this might fit into this and how you might be able to answer some of these questions that everyone is wondering about. Thanks for your attention. And I'll be also in a panel meeting on Tuesday and happy to answer questions then, or feel free to redirect questions to me at other times too.